Good morning, class. Can you hear me? My audio coming through?
Yes, sir.
Excellent, thank you. Okay, like I said, I will have some information up about the test that's coming up, and put your minds at ease about that. I appreciate all the hard work that you're doing. We are reviewing college algebra, but we're adding more information, so it's actually uh, a good opportunity to become even better at techniques that you learned in your previous class. So really what I want to be able to do today is to go back to some of the ideas that you covered in college algebra having to do with one-to-one functions. And then we're going to give a description and treatise basically on quadratic functions. We've studied the quadratic equation and quadratic form. And so now what we want to do is just focus on the function that we call quadratic and see that pretty much everything we know will apply to that. Just adding a few other details that will make the study of quadratics and their counterparts, quadratic functions, a little bit easier for you. So let me go ahead and share my screen. What I want to do today is basically just go through a few definitions. And I know that the definitions sometimes get a little bit boring, but we can't really do anything. For instance, when you think about compositions and you think about how we deal with the definition of a polynomial, how do we find the domain of a composition? We have to go back to the definition. So as my math professors used to tell me, they'll say, Ron, they say, if this isn't working, use the definition. So that's what we have to start with today. Now, what I want to focus on is first the one-to-one, and notice here I have inverses, and that's going to mean inverse functions. So inverse functions. And these, like the even and odd functions that we talked about at the last class, are very, very useful. But unfortunately, they are quite restricted. You know, we would love for every function to be even or odd so we know lots of things about it, or maybe we would really like for every function to have an inverse. That would be a perfect world. So unfortunately, that's not the case. But when we do encounter them, we want to understand them. So the very first definition is this one. Let me also say this about your WebAssign. There might be cases where they say, oh, with a graphing calculator or whatever, or use this. Ignore that. The problems can be done as I am teaching you. So don't take out some fancy calculator to work them. Unfortunately, sometimes those directions kind of seep in, thinking that you might be taking a class that Professor Ron is not teaching. So ignore all of that. I want you to do your work the way I show you. And if we need an approximation, fine, we'll do that. Just remember, all answers are exact. Any number you're given in a problem is exact. So if you're not asked to approximate, you give an exact response, always. Now, let's look at our first definition. It says the function of f is one-to-one if and only if, so we're starting with the function, if f of a equals f of b, then this implies that the inputs must be the same. So this is starting on the level of function, but it's a very restrictive definition. That is, if you have two elements that are equal in the range, it must be the case that their inputs are identical. So when you hit a value in the range of a one-to-one function, that's a one-time deal. That occurrence will never happen again. So what some students like to say, different inputs mean different outputs. So you can't have f of 1 equal 3 and f of 2 equal 3. That's not going to happen. That will violate this. So lots of times students will say, well, Professor Ryan, I kind of like when you turn it around and write it as a contrapositive to say, just as I said before, different inputs, different outputs. Now, I want to share just some ideas here about the inverse functions that I want you to write. If f is 1-to-1, then f defines an inverse function. Now, when I say inverse function, we're going to denote it with an f, whatever we're calling the original function, with a superscript -1. Now, when I say superscript -1, this doesn't mean 1/f, like, we'll say 2 to the -1 equals 1/2. That's just the definition of the negative exponent. But this is just the notation for inverse. So think of multiplicative inverse function. And this is convention. This is universal. Everybody writes inverse functions this way. So basically here, and we'll talk about these in an example, but I want to get through all of these attributes of these functions. The function f inverse defines a reverse path. So basically, as you go from a domain element to a range element, you know that there's only one path to that range element. No other element in the range will coincide with that particular number. And so you can go backwards. That is, you can just reverse your path and go back to the domain element because you know there's only one path. So basically, we say that f inverse defines a reverse path. And you might be thinking, well, that 1-to-1 function implies the reverse path. So isn't that just the same function, thinking about it backwards? And if you're thinking that, you're exactly right. But sometimes it's convenient to write the inverse function so we can do computations. So if that's the case, the domain of f will be the range of the inverse function, and the range of f will be the domain of the inverse function. They just flip. That's all, because again, if the inverse function defines the reverse path, you start in the range of f when you're in the domain of f inverse, and then the range of f inverse is just the domain of f. So it's easier just to say this, they just flip. Now, one notation that we like to use with inverse functions is this, and this basically talks about the inverse path. We'll say y equals f of x, and then we will apply f inverse. So if we start in the range of f and apply the inverse function, we get back to the domain, so to speak. The reverse path is this. So if y equals f of x, then x is equal to f inverse of y. Now, you might be thinking, it's probably good to preserve the letters that we use to denote the domain elements of f and the range elements. That's what we normally do when we do the ordered pair x comma y, just to keep everything really simple. But there are times, I'm going to show you in an example, there are times when we want to preserve this, and then there are times when we want to be a little bit more flexible. So, for instance, if we use the same independent variable for each function, we can actually define inverse equations this way. And what it means is that if the inverse function is the reverse path, it undoes f. So, thinking this way first, if we compose f with its inverse and apply it, in this case, to an element in the domain of f inverse, we go right back to it. So this is the case where we're just using the same element. And I don't particularly care for it because when I teach, usually I just say, let's focus on the x and y's, and then at the very end, we'll flip them just for convenience. And I'll share with you why we actually like to do that. And again, like I said before, usually when you compose two functions, they're rarely the same. If you do f composed with g and g composed with f, rarely will they ever be the same. They're really unequal in general. So here's this special case. If you compose f with its inverse function in either order. And like if, as we look here, f inverse composed with f of x. So again, we apply f inverse to f of x. We get the identity function. And what I mean by identity function is that the input equals the output. Like f of x equal x, the input equals the output. So these functions undo each other. They are inverses, so to speak. So again, you're thinking, well, that's pretty simple. If I only had a finite number of elements in f and it's 1-to-1, then I can draw the arrows forwards and backwards and get a real simple function. So that you might be thinking, why do we do this, Professor Ron? Well, here's the reason. If we think of it this way, that is, if A maps into B under F, if we turn it around to do the reverse path, B maps into A under F inverse. This is the reverse. So basically, if AB is a point on the graph of F or an element of F, the flip of that, BA, is an element of the inverse function. So, because this is true, graphically, we get that the F and F inverse are reflections in the line y equal x. That is, if you try to graph the functions, you will see that the y equal x is a mirror. Just like for even functions, the y-axis is a mirror. Just like for odd functions, the origin is a mirror. You get symmetry with respect to the origin. For functions and their inverses, you get symmetry relative to the line y equal x because you get this flipping of the coordinates. So when we want to graph a function and its inverse, it is convenient, as we know, to have the same independent variable so we can preserve this symmetry. So that's one reason why we want to do this when we're graphing. You can't have different independent variables and just ignore that when you work with inverse functions. So you're thinking we're flipping things around so that we can graph both of the functions on the same set of axes, and then this reflection property actually comes into fruition. So let's look at an example. All of these ideas right here, put on a note card, put them in your memory bank. We will use these over and over. This basically characterizes the inverse function and what we want to try to do. So let's look at an example. So I got some questions from some of you all. We can do some easy ones, but for instance, let me just start out with a really simple one. Say we have a discrete set, and we have, I'm going to write down 3 or 4 domain elements. I'm going to keep it really simple: 1, 2, 3, and 4. So the domain of F consists of those 4 elements, and they're going to map into these numbers. So we might say just very simple: 5, 6, 7, 8. This is completely arbitrary, but no problem. So we're saying that f of 1 is 5, f of 2 is 6, f of 3 is 7, and f of 4 is 8. Okay, well, by definition, this is 1-to-1 because we see here that no domain element maps into the same range element. They're all unique. That is, we see, for instance, f of A equal f of B does imply that A equals B. Or we can say if you have a different input, the output's going to be different. And in a discrete case, it's very simple. So you can always go back to a simple example like this and say, I got the 1-to-1. Now, the reverse path. So if you like, let's just go ahead and write this down. Domain of F will be 1, 2, 3, 4. And the range of F will be 5, 6, 7, 8. So I just picked nice, easy numbers, user-friendly. So now let's do the reverse path. I'll do this in red. And we'll call this F inverse, okay? So like I said before, the range of F now becomes the domain of F inverse. If this were any easier, it'd be too difficult, really. Inverses are simple. I mean, factoring is harder than understanding this concept. And then we see that the range of F inverse is the domain of F. So one-to-one functions define the reverse path. So the idea here is that we can look to see what's going on here. So for instance, if we say F composed with F inverse, let's just pick 4. Well, by definition, this is F of F inverse of 4. Well, F inverse, and oh, sorry, I need to, well, I guess I better actually pick an element that's in the domain of F inverse. So let me choose 7. Yeah, that would be correct. Math is self-correcting. I mean, this wasn't even defined. That'd be a terrible question on a test. That'd be a trick. Okay, so now F inverse of 7, that equals 3. So we have F of 3. And of course, F of 3 is 7. So like I said before, the composition of F with its inverse is the identity. Input equals output. And of course, if you flip it around, it's the same thing. So just remember, you know, this is like what we said before. You know, if I don't put a number here that's in the domain of F inverse, then it won't make sense. And I'll just say void, no answer, void, no, this doesn't make sense. It's not defined. So the beauty of the mathematics is that it will always correct you as you work through. Now, one thing that I want to do here is just do a little point plotting deal. So we'll say F is 1, 5, 2, 6, 3, 7, and 4, 8. And then, of course, F inverse is just the flip of all of these. 5, 1, 6, 2. So now when you do all these simple problems on WebAssign, you'll be a master at them. I want to start out with the basics. So you just flip all of these around and you get elements on F. So now we could just plot these. That's why I chose some simple numbers here to make a simple plot. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So let's do this. 1, 2, 3, 4, 5, 6, 7, 8. And then the same here. 1. I'll try to do it as even as I can. 2, 3, 4, 5, 6, 7, 8. So now, if you will, let's go ahead and kind of eyeball this to get the y equal x line. So this is y equal x. So let's go ahead and plot. I'll plot the F in blue. So we have 1, 5. So if you like, so we got 1, 1, 2, 3, 4, 5 right here. So I'll mark off some of these as I do them so you can see what the scale is. And then we can do 2, well, and let's go ahead and just do them in interchange. Let's do 5, 1. So now 1, 5, and then 5, 1, 1, 2, 3, 4, 5, and a 1. And now let's do 2, 6, 2, 6, and now 6, 2, and now 3, 7, 3, 7, and 7, 3. And then 4, 8. So I'm up here in the stratosphere. And then 8, 4. So what we see, even though my picture's not perfect, we see that these points are symmetric relative to this line. That is, now, if we dotted right through here, this distance equals this distance. 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 So again, what we're seeing here is that we get this y equal x to be a mirror. So what we want to do is utilize the fact that we think of the first coordinate as being x and the second coordinate as being y. So in the very simplest case, this kind of characterizes everything that we need to know about inverse functions in the discrete case. So we get this nice mirror image between the graph of f and f inverse in the line y equal x. The range and domain interchange. One-to-one functions define inverse functions. So, I mean, f has all the information in it. F defines the inverse. So we just add to the amount of material here by strictly defining the reverse path. Even though f defines it, it's implicitly defined. We want an explicit version of it, and that tends to be extremely useful in mathematics. So mathematics likes to talk about inverse functions. So let's look at an example of a function that may be defined like a formula. So in this case, we've got a good idea here of what's going on. What we want to do now is now look at a function that's defined in terms of a formula, because you're going to be taking calculus, and that's pretty much how things are going to be defined. But I want to set this up so you get a good feel for what an inverse function is. So now f of x, let's start with this. This is right from your WebAssign. It's similar to a question that I was asked about with compositions. You really do have to pay attention to the definition of composition to be able to compute domains of compositions. At first, it seems a little strange, but it will ease. So what I want you to do here is let's prove that f is one-to-one, and then let's write the inverse function like we did in the previous example. But here's the thing, we can't, in this particular case, we cannot, let me move the mouse over here. I don't want to put it somewhere where it's going to cancel something. Oh, I don't use that word absorb, I should say. So what we want to do here is prove one-to-one and then come up with the formula for the inverse. So prove f is one-to-one. Now, of course, in the WebAssign, if a function is one-to-one, that is like the vertical line test for the definition of a function. You have the so-called horizontal line test. Well, let me just make this comment, ladies and gentlemen. If you know what the graph of a function is, then you understand the function. So you can't graph a function to decide if it's one-to-one. That's a circular argument. If you understand the function, you know what its graph is. That's what you do in calculus. So again, I want you to be able to look at a picture of a function and say, oh, that represents a one-to-one function. But you cannot use that technique to prove that something's one-to-one. That is circular, and that's probably what you drew from your college algebra class. And I want to help you improve upon that. So prove F is one-to-one and compute F inverse. Now, and I'll say here, we'll probably go ahead and flip around the X's and the Y's. I'll show you how to do that. So first, we assume, so we'll just use the A's and the B's, F of A equal F of B. You can use any letters you like. We just have to show A equals B. Now, of course, if I ask you to do this, then it'll be something you can solve. Okay, we won't have to step up to some of the methods in calculus. So replace X with A, so we get A over A plus 4. And now replace X with B, so we get B over B plus 4. So now this is good old cross multiplication. So, or invert and multiply. So we have B times A plus 4 equals A times B plus 4. Now we can distribute, so we get AB plus 4B equals AB plus 4A. Now, of course, the AB's absorbed. So we're done with that, and we get 4B equals 4A. And then, of course, the 4 is absorbed, and we get B equals A. So by definition, F is one-to-one, but you probably already thought that. I've used examples similar to this before. So you're thinking, well, okay, what did we not do? We assumed that we have a one-to-one function. I'm asking you to prove that. We just did. So this implies F is, and I'll use the shorthand 1-1 because we're lazy, 1-to-1. Now, we might as well go ahead and write this down. The domain of F will just be all real numbers except -4. That's how you do the compositions. You start with the inner function first. So we can't divide by 0, so we get this. That's why I've talked about these functions before. It's important. And now, of course, if we look at this function, we can see that the range could never include 1. So the range of F excludes 1. And now, of course, this just flips. We know the domain of F is the range of F inverse. And the range of F is the domain of F inverse. Okay? Now, this is a rational function, and it's got asymptotes. And so we won't graph it right away. You can if you like, but I will hold off on that till we review the graphing of rational functions. That'll be quick, but I don't want to spend a lot of time on that right now. If you want to go ahead and do that and see the symmetry property, that's fine. Remember, the horizontals become vertical, etc. Everything flips around. Now, what we can do is say, okay, we've got this formula here that is equivalently y equals f of x. So y is equal to x divided by x plus 4. This is why I did what I did last week. And we're thinking, how can we get the reverse path? We have y equals some formula with x, but we need to go backwards. We need to start with the y and get the x's. So we need to solve for, in this case, x. Solve for x. So this says input an x and output a y. But in the reverse path, we need to input a y and output an x to go in the opposite direction. So that's what we need to do first. Do not switch the letters. Some of you know that. Unlearn that. That is not how you do it. We want the reverse path where we actually solve for x. So that's the first thing. So cross multiply. X plus 4 times y equals x. So now we have 4y here plus xy equals x. So we want to solve for x. So let's get all of our x's on one side. So I don't know, we could just take them over to the left. So we have xy minus x. And I'll take this over here. Of course, we'll divide and multiply by -1 if we have too many negatives. So take the 4y over and take the x over. Now we can factor x, y minus 1 equals -4y. So now equivalently, we can now solve for x. X equals -4y divided by y minus 1. Now, if you don't like all of those negatives hanging out, you don't have to live with them. So what we can do is multiply and divide by a convenient 1. That is, multiply and divide by -1 to flip everything around. So x would be 4y over 1 minus y. So that's the reverse path. Now you input a y and you output an x. So this is the reverse path. Now this is probably favorable when you're doing word problems and you want to keep the x's and the y's separate, okay? But now if you want to think about the symmetry property with the graphs, we would need to interchange. Again, just remember when we change the letters, we're not really changing the function, but you see here, if we need any restrictions in our problem, we want to preserve the x's and y's because the restrictions will be based on the x's and y's as they exist in the original function. So you don't want to start switching things around and get confused. But notice here, we don't have any restrictions that we have to apply. So now we can there's our inverse. We can say this is just f inverse of y, writing the inverse function in terms of the letter y. But now, of course, if we want to graph on the same set of axes, we can just replace the y's with x's. And so we can define the inverse function this way. This is preferable, but this is popular, what I'm doing now. So we have 4x divided by 1 minus x as our inverse function. Now, what I want to focus on here is to make sure that you think about the concepts that we've done here. I want to do an example where we actually consider sticking with this, but I want to do one more problem where we just deal with maybe having a restriction based upon the problem and then work that forward. But notice now you can see here the domain of f inverse must exclude 1, as you can see here. It has to. There's no way that would be undefined. And then, of course, the range, in this particular case, when you compare the leading coefficients, -4 would be kicked out. So you can use this computation to kind of verify that you did everything right in your formula, okay? So let's try another one. Let's think about what we did with the transformations and do the same process again. But these would be a little bit easier to graph. Now, again, if you just know everything on the first page that we started, you know inverse functions, and just doing the problems will just make you even more adept at it. So let's say we have f of x, and of course we're lazy. We call everything f of x. I mean, we could call it g of x or g of any number letter if you like. Let's do this. Okay, so we're going to start out with this function. Now, when we look at this function, let's go ahead and do domain and range. So what I'm going to say first is prove f is 1-to-1 and compute f inverse. All right, so before we do that, let's just go ahead and do a little bit of college algebra, that, you know, domain, range, something like that. So we'll say domain of f will be all real x such that 3 minus x is non-negative. So this is imposing a restriction here that that was unlike what we had in the last problem, even though we did exclude a number. So this is all x, and so this will be x is less than or equal to 3. That is, we just transpose the x, and that makes sense. This can be 0 and anything positive in the argument. So we'll have to get smaller. So basically, this is just negative infinity to 3. After those word problems and all that symbolic computation, we're getting a breather. But that number theory that we practice is excellent to keep you sharp. So I'm glad that you all have spent time on that. But now if we look at this, the domain of f is the range of f inverse. This always helps us out if we're going to try to get a cheap graph of everything. It just kind of helps us check that we've done things correctly. And then now, of course, by definition, this is just the principal square root, and it is either 0 or positive. So just by definition, the range of f will be 0 to infinity. But then that's the domain of f inverse. They just flip. Whatever, if you put range of f here, you put the opposite domain and then f inverse. Domain of f is range of f inverse. Okay, so that's not hard. That's just interchange. Now, so we've done the easy part. We need to be good at computing domains and ranges, or at least domains. So now we want to prove. So 1 to 1. So let f of A equal f of B. So you're thinking, well, that's a transformation, Professor Ron. Let's just say, we could say something like this: factor the negative x minus 3. So if you looked at this, if f is actually written this way, you'd say, oh, okay, well, I can reflect the graph in the y-axis, replacing x with its additive inverse, and then do a right shift by 3. So we could say this is x, y-axis reflection, and then replace x with x minus 3. So that would be how we would unravel the transformation. So that's a previous lecture problem kind of tied up in that. So that kind of tells us what this needs to look like. So that we got that for free. So now f of A equals f of B. So we'll have what? Square root of 3 minus A equals the square root of 3 minus B. So we're at the point where if we need to figure out anything about this problem, we need to square both sides to eliminate the radical. So if we square, we get 3 minus A equals 3 minus B. That is, if these two radicals are going to be equal, their arguments will have to be the same. Well, of course, now the 3's absorb, and we get negative A equals negative B, and then the negatives absorb, and we just get A equal B. So F is 1 to 1. Okay, so if you drew it, it would pass the so-called horizontal line test if you drew the graph. So that's what tells us that it's 1 to 1. So now just remember, when we look up here, we have this nice restriction here. That is, we see in the domain of F, we must have this, in the range we have this. So we may have to use that information. So now let's solve. So we have y equals the square root of 3 minus x. And I thought maybe I was too simple on you. We don't have to use the square root property here. So I've made the problem too easy. Okay, so now if we want to what? Solve for x. So square both sides. Y squared equals 3 minus x. And so now, of course, we want to solve for x. So let's take the x over and the y squared over. So x equals 3 minus y squared. And that's another transformation, a reflection in the x-axis, and then bump it up by 3. Now, of course, this is F inverse of y. Now you can see why it is convenient to now write the inverse function with the same independent variable so we can graph them on the same set of axes. So there is a method to the madness here. But again, this preserves what we had before. Now we input the y and we output the x. Here, when we started with this, we input the x and output the y. So now we'll say let f inverse of x, we just now switch it out, will be 3 minus x squared. So just for convenience, ladies and gentlemen, we do this. This is really what gives us the information we need, and we really relish this, especially with word problems. If you're doing a science problem and you're solving for an inverse, you need to keep the variables separate. So because the variables may represent certain items in your science problem, and you go around flipping them, you don't know what's going on. So many times we have to preserve this just when we're doing problems where these variables actually represent certain quantities. So now, if you want, let's just go ahead and be lazy. Now, if we go up here, domain is what? Negative infinity to 3 when we look at this. So let's go ahead and graph. So what we can do in this particular case is we can think, okay, well, if the domain here of f inverse, oh, excuse me, if the domain of f inverse is 0 to infinity, that's going to help us out. Let's first get some cheap points here. So now notice here, if we input 3, we get 0. So we'll say 3 comma 0 is an element of f just by looking at that. So basically looking here, and then of course that would say that 0, 3 is an element of f inverse. And now, you know, and this is just to get a few more points here, just so we have a nice graph. When does this equal 0? Let's get another point. Let's just say we have, well, we got the 0. Let's do this. We could look at this and say, okay, well, is there a simpler number that we can substitute? With this, let's just go ahead and see what we have here. If we do 3, 0, let's go ahead and mark this off. 1, 2, 3. And then we could say, if we want the point here, let's just do f of 0. That'd be an easier way of looking at it. F of 0 will now be the square root of 3. So we have 0 root 3 element of f, and we have root 3 comma 0 element of f inverse. So we can kind of guesstimate. So 1, 2, about, you know, 1.7, about right there. So now we know what this looks like. This is just the square root function. So we're going to go ahead and draw it. So let me get my vertical tangent going. So like that, a vertical tangent. So this is f. And now we can do f inverse by just with the flip here. So f inverse, we have 0, 3. So 1, 2, 3, about right there. And then we have square root of 3, 0, about right here. So that's going to give us our reflective property. So mirror image. So I'm going to turn this so I can draw it. So we've got basically a parabola here. So this is F inverse. Now you don't have to be Rembrandt here. Obviously Professor Ron is not Rembrandt. And what we're looking at here is now we can see, of course, if they cross the line y equal x, the values have to be equal, clearly. This is y equal x, input equals output. So what we can see here is in this particular example, we can illustrate, like we did with the discrete problem, that we definitely have symmetry between the graphs. That is, f and f inverse reflect in the line y equal x. So what I did here was I just looked for some simple points. I've got a x-intercept and a y-intercept and then flipped them around, and then use the fact that I know what the shape of these functions happens to be to draw a picture. So that's really what we want to be able to do here. Now, like in the WebAssign, they might say, well, you know, pick the graph of f inverse, and or pick the graph which displays f and f inverse. So this is the kind of computation you would do. You wouldn't necessarily have to draw everything out. You could say, okay, well, this is what's going on. And now when I compare this, we have what? So range of f inverse, where are we? Right here, negative infinity up to 3. So here's my 3 here. And then, of course, the range of f is just what? 0 out to infinity. So all of this checks out. And of course, here's the 3 here. And here we have square root 3. And here we have square root 3. Just plotting the points on the axes. So again, the nice part about this is that we can use our understanding of transformations. We can use our understanding of inverse functions to just generate a few points, 2 points, and then use symmetry to actually sketch the functions. So this is, you know, you don't do this every time, but it helps you to understand the reverse path and why when we actually do a computation, when you do some of your word problems, what you're going to do is you're pretty much going to stop here. There's a pizza problem and a Fahrenheit problem, you know, that's really straightforward. The inverses are easy to solve, but we will want to preserve this so we can figure out what the x's and y's represent relative to the problem. So when we're interested in doing word problems, we usually like to stop here. But when we're going to go ahead and graph both functions on the same set of axes, we need to make this statement so that we have the same independent variable. So again, the beauty of the inverse function is that it's actually quite simple. The difficulty is that we might be dealing with functions in calculus that are actually invertible if we restrict their domains. Clearly, this function here, if the domain weren't restricted based upon this one-to-one function, this would just go this way and be a nice quadratic function, which would clearly not be one-to-one. So the idea here is that what I started out with was a nice one-to-one function that offered the restriction that we need. So when we get to the domain of f inverse, here's the restriction that makes this blue function one-to-one. Because if it weren't there, this would actually come over across this way. And of course, that's not one-to-one, but it's all built into the problem. So again, one-to-one functions and inverses are very simple if you just have the basic rudiments. That's all we're interested in. And as you work your WebAssign, just be sure if it's a word problem, just to preserve the inverse function like this. And the problems are really nice. Remember, everybody, they will write down the formatting of what you're supposed to type. So maybe they'll say f inverse of y. So you stop here, okay? Or f inverse of n or something. Okay, so always follow the formatting. And just remember, science requires that we keep track of the variables. We can't be as flexible, all right? So one-to-one functions and inverses, easy or less difficult. Now, what I want to do is say a little bit about some quadratic functions. Now, the idea with the quadratic functions is that we pretty much know everything, but we just want to tabulate all of the different ideas that we have, and they're not many. So this will be 3.1, and this will be the last section for the test, quadratic functions. Now, this should remind you of the terminology that we used with the quadratic equation. So the definition will be this. We will let A, B, and C be real numbers. We're just going to basically right now look at quadratic functions that have real coefficients, that is real polynomials like this. So we're going to look at A, B, and C being real numbers, and then where, just like with the quadratic equation, A is non-zero. I mean, let's face it, ladies and gentlemen, if A is 0 in our setup, then the quadratic term is missing, and that's no good. So we define the quadratic function. Make that a little clearer here. We define the quadratic function as f of x, and so this will just look like the quadratic equation without the 0. Ax squared plus bx plus c, where x is a real number. And of course, we can restrict it if we want. We can restrict the domain and get something that's useful. Now, when it comes to working with quadratic functions, there's certain things that we can actually tabulate. That is, you can always complete the square. Now, the interesting thing is, and students always get mad at Professor Ron, this is one standard form right here. This is one standard form. Now, sometimes WebAssign will say write in standard form, and they're meaning the second one that reveals the so-called vertex. So here is the, well, you know what? Let me just call this the first. So here's the thing, if you start out with this and they say write the standard form, don't type this again, because that's clear. They mean this one. And here is the second standard form. I had students during the summer, it was kind of hilarious. I said, wouldn't that be great if the answer was just what they gave you? But they were going on this standard form here. And I said that you're exactly right. That's a standard form, but let's get the second one, second standard form. So they were like, touche, you know, there are all these standard forms. So this is what this one looks like. We can say f of x equals, we basically complete the square. Complete the square. And so we preserve the a, but when you complete the square, we generate an h and a k. Minus h quantity squared plus a k. So this is like the equation of a circle. This is the second form. Now, what's interesting about this, and here are the attributes here. So number one, B, the point B with coordinates h and k from this equation is the vertex of F. Just like in the previous problem, we had a vertex. It was what? 0, 3. I mean, if you think about it, right here, that's the vertex right there of that quadratic function. So if you complete the square and write the second standard form, the h and the k give you the vertex. There's also a formula for the vertex. And we'll say, and here's a little extra, I'll call this 2. You can also write h as the negative of b over 2a using this form, like doing the quadratic formula. You pick off the b and the a, and you can do this, and then k would actually be the image of that, f of minus b over 2a. So this is extra. So you might think, well, you know, gosh, if I complete the square, I don't have to do this, or maybe I'll just do this. Your choice. It just depends. If the problem asks you to do this, you do it. And again, there's certain benefits for having the function in this form, just like there are benefits for having the function in this form. So 1 and 2 are related. Number 3, a greater than 0 implies k is the minimum of f. So in this case, a positive, as we didn't see in the last problem, means the graph will open upward. So we get a minimum. A less than 0 implies k is, and when I say the, because it is absolute, is the maximum, as we saw in the last problem, maximum of f. And I'll just add to this, graph opens upward. Graph opens downward. And in each case, and this is probably kind of obvious, number 4, the graph of f is a parabola. This is actually a conic section, and we'll talk about that later in the course. The U shape, so to speak, something like this, as you know, well know, etc. That's actually a conic section. And another attribute for 4, the vertical line, x equal h, and then we do conic sections, the graphs may open to the right and the left, and so we'll have a horizontal axis of symmetry. X equal h is, and I'll just say this, is a symmetry axis for f, is a symmetry axis. So it's like the y-axis being a so like, for instance, the vertex is down here and you put the vertical line here, you get x equal h. It divides the graph into 2 symmetric pieces. So basically here, you're thinking, okay, this just gives me some extra information about the quadratic function. Namely, if I complete the square or if I don't, I can figure out the vertex. The vertex will define a minimum if a is positive. It will define a maximum if a is negative. I already knew this. Well, I think we already knew about the shape. And then, of course, the symmetry axis probably knew about, but maybe didn't think as much about it. So the idea here is that with the quadratic function, we don't have a lot of new material, but we maybe think about the function a little bit differently. So we're thinking now, as opposed to just a quadratic equation, we might say, well, how will we do all that stuff with the quadratic formula and factoring? Well, now we can look at this and say, well, if you need x-intercepts, you can solve it, factor it. And you're thinking x-intercepts here would be maybe a little bit easier if you use the square root property. So all of the equation solving will be exactly the same as we've done before. we now treat this as a function, as a machine, and we apply everything we know about the quadratic equation to it. But this pretty much showcases it as a graph. And how do we graph it? And so if we do not restrict the domain of the quadratic function, it is clearly not one-to-one. So the only way we can actually make a quadratic function one-to-one is to restrict it. So I keep going back to this. This blue function is one-to-one because the domain is necessarily restricted by the original function. So like I say, this is a restricted domain. If it weren't, it would come this way, and clearly you'll have occurrences of outputs, two of the same outputs in the range, which violates the definition of the one-to-one function. So let's do an example here. So we have a little laundry list of ideas about quadratic functions that are really pretty simple. So I've got an example here. I've got a couple from your WebAssign. So let's just look at an example here. So, and do all the work that we would do with it. So we'll start out with this one. Now, of course, if you're given a quadratic function, the questions might be, for instance, compute the vertex, complete the square, compute the vertex, find the intercepts. So we have f of x equals 2x squared minus 4x minus a 3. That's a quadratic function. So here's what I'm going to ask us to do. Complete the square. So that would be the second standard form. Vertex, let's compute the vertex, and intercepts, x and y. So let's understand this function. And then, of course, if you like, axis of symmetry. So really, you already know how to do this problem. You already know how to complete the square, but now we just want to formalize it. So all we're doing is maybe making this function a little bit more formal. So first, what we want to do is complete the square. So we need monic. So we have to look at these two terms. So f of x, the leading coefficient is 2, so we'll factor a 2 out of these two terms. So we have 2, and the numbers are user-friendly, x squared minus 2x. And then just put some space here and minus the 3. So notice 2 times the negative 2x is the negative 4x, and 2 times x squared is 2x squared. So when we complete the square, we make monic, that is, this is a 1, and then we take half of this. Half of negative 2 is negative 1, and we square it. So we get plus 1 minus 1. So again, what we do to complete the square is we take half of this coefficient, in this case, negative 1, and square it. And that gives us the completed square form here. Notice this is now a perfect square. So over here to the side, we see that we do negative 2 divided by 2 squared, and that's negative 1 squared. So that equals 1. So the 1 here, we add and subtract. That's how you complete the square. And now we're thinking, okay, well, this is the perfect square. This is 2x minus 1, quantity squared, that part. And then, of course, here we have 2 times the negative 1, which is minus 2 minus 3. So we get 2 times x minus 1, quantity squared. And I'm just going to write this plus a negative 5 so you can see what the value of k is. So now when we look at this, we have a standard form, the second standard form. I put the plus here because I'm trying to remind you that this is now A times X minus H quantity squared plus K. Of course, students will say, well, I'm not going to put the plus minus. I'll just write it with a minus. But just remember that you are taking this relative to its sign. And the H must be taken relative to the negative here. So if you've got a plus here, you have to put in two negatives. It's just like doing the equation of a circle, okay? So now we can see when we compare the two, this implies that the vertex will now be 1, -5. So what's interesting about this particular problem is we can always manipulate the minus b over 2a, and we can do f of minus b over 2a. But what's nice about this particular setup here is completing the square gives us a nice form that we can use to find intercepts. So now we've got the vertex, and of course the axis of symmetry is a freebie. So x equal 1 is the axis of symmetry. So again, I want to impress upon the fact here that really the only thing that you need to review is when you complete the square, you create a monic polynomial. That is, if the coefficient of x is anything but 1, you factor that from the first two terms and move the constant, if it's there, over to the right, add and subtract the b coefficient here. Once factored, once this is monic, divide by 2 squared. That completes the square. This technique will allow you to complete the square. But then remember, when you multiply through, that you've got to not forget this term and add it to this term. So the completion of the square is actually a useful technique, which you will use in Cal 1 and probably a lot more, well, with certainly a lot more in Calculus 2. So now let's just go ahead and get our intercepts. Let's do x-intercepts, just to practice. And if you like, we can also say here that A is positive. Let's just go ahead and add to that. Here, A is positive. So this implies that -5 is the minimum because it opens upward. Might as well just add that. And I'll just say minimize. What's the minimum value? So you can look at a quadratic function and answer all kinds of questions. And maybe the problem just says find the minimum, or find the minimum or the maximum. You have to decide which one it is, and then you type that in your WebAssign. So that might be the only question that you have about a quadratic function. And so you can either what? You can do the minus b over 2a and then substitute that into the function, or you can just complete the square and boom, it's right there. There's my k, that's my minimum in this case. Now for the x-intercepts, we're thinking we just need to set f equal to 0. We need to see if it actually crosses the x-axis. So now since we bothered to complete the square here, let's just go ahead and use this. So this just says f of x equals 0. So let's just go ahead and use the completed square form. We did all the work. So we have 2 times x minus 1 quantity squared minus 5 equals 0. So let's go ahead and subtract 5 from both sides. 2 x minus 1 quantity squared equals 5. And now divide by 2. X minus 1 quantity squared equals 5/2. Now at this point, we have something squared as a real number, so we use the square root property. X minus 1 is equal to plus or minus the square root of 5 over 2. Now, I like exact, and of course, if WebAssign asks you to approximate, that's fine, but just do it at the very end. Don't approximate in your problem. So now we have x equals 1 plus or minus. Now let's go ahead and rationalize this because we want to make it look pretty. That's fine, but you can write it as an actual fraction with the denominator. So we'll just multiply and divide by square root of 2. So this would be square root of 10 divided by 2. So just recall, if you have root 5 over root 2, you can multiply and divide by root 2 if you like. And that'll give you root 10 over 2, just to rationalize. I don't really care about this, but this will actually allow us to write these intercepts in a maybe nice fractional form. So now this would be 2 over 2 plus or minus square root 10 over 2. Your choice. If you left it that way, it wouldn't matter, and I'm fine with it, but just some practice. And so now we get x equals 2 plus square root 10 over 2, and we get x equals 2 minus square root 10 over 2. So that just gives us our x-intercepts. Again, very, very straightforward, but good practice for the test. Again, you could just start here at the top and use the quadratic formula, but since we bothered to complete the square, why not just do it this way? So we've got all that work. So we go forward to go backwards. And then, of course, the y-intercept. So these are our x-intercepts. Y-intercept is easy. We certainly don't want to use that. We'll go back to the original. That's just f of 0, and that equals -3. So when you think about this particular function, you're thinking, you know, what do we have here? So if we wanted a cheap, really cheap graph, we could say square root of 10 is, say, approximately, you know, we'll just use 3.2 just as a rough estimate. So now here we'll have what? 2 plus 3.2 divided by 2. So this gives us 5.2 divided by 2. So if we approximated that, that would be a 2. So we'd have it say like a 2.6. Again, rough estimate. We just want a cheap graph. And here we'll say this is approximately 2 minus 3.2 over 2. So this gives us a negative 1.2 over 2. So this will give us a negative 0.6. Well, let me bring that up a little bit. So we just do a rough estimate to get a reasonable picture here. Let me get rid of that extra down there. Okay. So if we want, like I say, a cheap graph, let's just do a cheap graph. So here, so we want to go down to -5, so I'll have a little space here. So we'll do 1, 2, 3, 4, 5. And we'll spread the y-axis out, or the x-axis out just a little bit since we've got a 1. So we'll do like a 1 and a -1. And then like a negative 0.6, right here. And then 2.6. About right here. So let's see, yes, 112, there we go. And then now we've got 1, -5, about right here. And so let's see here. So let me just check this. 5.2, you got a 1, so got a 2 and a 12 here. That looks good. And here, that looks good. Oh, and then we'll cross through the -3, the y-intercept. So now our cheat graph, we have -3. Here, we have this guy, 2 minus root 10 over 2. And here, we have 2 plus root 10 over 2. And if you like, our axis of symmetry. So this x equal 1, and the vertex v 1, -5. So when I say cheat graph, we may not actually get nice numbers for the x-intercepts. The y-intercept is a piece of cake, but we may have to do just a little bit of an approximation here. But notice we do that once we have our exact values and we can get a reasonable sketch of this. So in general, quadratic functions don't present simplicity when it comes to intercepts at times. However, we completely understand them. We know everything about quadratic functions. We know their shape. We know their calculus. That is, we can find the maximum or the minimum without a derivative. We know everything about these functions. And so because we have quadratic form, we have the theory of the quadratic equation. The quadratic function is like, wow, that if our function is quadratic, then we have all the information we need. We can figure out all of this. So you might be doing a problem where all you need to do is graph the parabola, but that pretty much, or the quadratic function, and that would pretty much mean that you would have to go through all of this. So this would be the most tedious example, but it could be, okay, find the vertex, find the axis of symmetry, maximum or minimum, okay? So another thing too, and you might notice with this particular problem, say you're doing a WebAssign problem and they say, well, restrict the domain. So once you find the vertex, that can allow you to restrict. So they'll say restrict the domain so that f of x is 1 to 1. So for instance, we could restrict 1 and greater or less than 1. So for instance, restriction. Here's just a hypothetical. Maybe they tell you what the restriction is, or they say, here are a list of restrictions. Which restriction makes f1 to 1? So 1 would be x greater than or equal to 1. So if x is greater than or equal to 1, you just get this branch here. So x greater than or equal to 1, f is 1 to 1. Or maybe we want to do less than or equal to 1 to get this branch. Less than or equal to 1, f is 1 to 1. So you can make up your own models, and you can restrict as you like using the vertex. The vertex will just give you the axis of symmetry, the H. And if you go on one side of the H or the other side of the H, you get either of these branches. And these branches, as we know, are 1 to 1. We saw that in the problem that we did with the 1 to 1 functions. So again, what's important here is that nothing that we have done is new. All of the techniques are old math, but now we're combining it in a way so that we can treat this as a standard machine, as a function. And so again, as you do the problems in 3.1, they're all going to circulate around the types of calculations we've done here. And some may be very simple. Now, I will say this, the minus b over 2a construction or computation is fine, but I do want you to get some practice using the complete the square. I think that's a really, really good thing to know how to do. And the more practice you get with it, the more you'll master. Okay, so I guess we beat that function up. I want to give you some examples of how this would relate with word problems, like I was saying with the one-to-one functions, even though those might be a little bit easier. Um, when we do problems, for instance, if we have the absence of a constant term in a quadratic function, we know it's easy to compute the intercepts. That's so easy. We know one of them is going to have to be 0. So let me give you a simple example here, but a very important example. So we'll say R of X equals, and we'll just use some factoring and symbolic calculation, which is good to do. R of X, that's going to be revenue, is going to be 2/5 X squared, where R is measured in dollars. And X represents, this is just a little bit of dialogue, X represents the number of units manufactured. So we were thinking of revenue. Okay, we've done this before. We've had a problem like that before, and that was a great word problem in 1.8. Nice symbolic computation. So what the question is here, again, here are the questions. And so you're thinking, okay, Professor Ron, that's a quadratic function, and it has no constant term. So this is a quadratic function. So we'll say this, here are the questions. What is the maximum revenue? And then also compute X. So this is compute X. Oh, let me just say it this way. That way the way I've written it there, it seems like that's what I'm asking you to do in the first part. And we'll say this, how many units should be manufactured? So when you look at this problem, you're thinking, oh, I see, Professor Ron, we need the vertex because the maximum is the K. This is the K, and the number of units is the H. So we need the vertex. Now I want to show you a little trick here that is actually very pleasing. That is, there is no constant term here. So when you have X intercepts, and I will show this on the last problem, when you have X intercepts here, the segment that is created by the intercepts is bisected by the H from the vertex. So for instance, if you know the X intercepts, you can just find the midpoint and boom, there's the H. Just by the geometry. Very simple. So this opens the door to another technique that you can utilize. You don't have to, but this is actually quite valuable. So now we can just say, all right, let's rewrite R. So R of X, let's rewrite it with the square term first, and we just want to factor it. So now let's factor, we got an X and a negative 2/5 that we want to pull out because we want the X inside to have coefficient 1. So we have this. So now notice that we've extracted the negative 2/5 and the X from the first term. So that just leaves an X. And now here to compensate, we'll just flip it. We'll just say plus negative 5 halves times 80. Of course, we've taken out the x, that's been extracted, but we have to pay for the negative 2/5 by reciprocating it. So when we multiply back through, we get exactly that term, and we have the negative times the negative, and everything works. But now we have negative 2/5 x. Now notice here we have a minus that's built in. So we have a 2 into 80, that's a 40. And then we have the 5. So just symbolic calculation. So that's a what? A negative 200 or a 200 with the minus sign. Now, you're thinking, what could be easier? Just by doing this basic factoring here, we now can see that the intercepts are just 0, which we get for free. We know that one of them's got to be 0. We just have to add the other one. We get 200. So we'll say this equals 0 if and only if this is just 0 product, x equals 0 or x equals 200. So midpoint will just be 0 plus 200. Remember, we take the average of the intercepts divided by 2. The midpoint's getting some use in this class, especially when we're doing the symmetric intervals with the conjunction. This is 100. Now, you're thinking, well, Professor Ron, this does the problem backwards. Since we didn't complete the square, we're getting the h first. So this is the h. So that's the number of units. But here is what's nice about this. With this nice factoring here, we can easily compute the image of this. So this gives us the number of units, the h, and so now k, which in this case will be the maximum, will be r of 100. So you might be thinking, I like this. This is okay. I mean, you have your choice here. You can do minus b over 2a, but when the numbers are messy, you have chances to make all kinds of mistakes. Well, of course, you could make all kinds of mistakes here, but that's why we practice. So now we can go here and say we've got negative 2/5 times 100, and then we have 100 minus 200. So at least if we bother to factor, it certainly makes the computation here easier. So what does that give us? So now we have two negatives. Well, we've got negative 2. And then, of course, 5 into the 100, that'll give us a 20. And then, of course, here we get a negative 100. So this will just be 40. The negative is absorbed times 100, which is 4,000. And so this gives us the maximum that we're looking for. So now we see that we can analyze this quadratic function, we can find its maximum and the value of x which attains that maximum. So in calculus, you'll say, what is the maximum of this function? You'll say 4,000. And then you'll say, at what element of the domain does it occur? You'll say 100. So again, the beauty of this problem is that you could complete the square, which is fine, but I think this method here actually takes you right back to the 0 product. And a good factoring technique, that you're doing a presentation and you might say, okay, well, ladies and gentlemen, I've now have a nice function here that's easy to evaluate. And if you like, you can use the axis of symmetry to make the calculation simpler. But now we have a form for R that's easy for computation. This is a train wreck up here. That's too complicated. I mean, we could factor the X and make it simpler like we've done here. See, when we do this type of calculation, we make the polynomial user-friendly. That is, now it's so much easier to compute this than to compute that. Computers don't like this, they like this, and our brains like this. So when we transform the actual function into a simple form, not only does it give us information, in this case, the number of units that need to be produced, the h of the vertex, we can now find the k just by simple substitution without having to do anything complicated like squaring and getting larger numbers. This is much easier. So what I'm trying to show you is that the symbolic calculation technique from the word problems can be extended to this. So factoring and looking at something in a different way gives you more information. Now, let's try one more. Again, I want you to take this information today basically as review, but maybe you've learned some things and some ideas that make your work a little bit easier, and maybe have added to some of the ideas that you learned in previous classes, and you can take them to the next level, so to speak. So now, here's the next problem. We've got, I like this particular example in this particular case. It talks about, you don't actually construct the actual, well, we can construct the function, but it has to do with a farming type situation where we're looking at maximizing, in this particular case, the number of trees per acre. So let me write this. Yes, so if n as a variable, n trees are planted per acre, if n trees are planted per acre, then the tree produces, that is, we're thinking about maybe an apple orchard, then the tree produces 1,870 minus 17n apples. So I could actually write this problem in a different way. So, but I'll just go ahead and write it the way, you know, kind of a paraphrasing from WebAssign. If n trees are planted per acre, then the tree produces this many apples. That is 1,870 minus 17n apples. So what we're seeing is that if you increase the number of trees planted per acre, the output of the tree goes down in that particular acre. So you don't want to plant too many. And so then we could say, here's two questions. How many, well, I'll just say, let me write it this way. I'll make a formula question out of it. Write a formula A of n that represents, I just wanted to write this problem in a different way, that represents the number of apples produced per acre. So write a formula A of n that represents the number of apples produced per acre. And then I will say maximize A of n, just like we maximized the revenue in the last problem. So again, I've paraphrased the problem in WebAssign, so maybe you could think about this a little bit differently. So if we plant some variable number of trees per acre, then the output per tree is this. And so the apples produced per acre would now just be A sub n or A of n will just be the output per tree times the number of trees, right? So we're like, oh, how nice is this? It's already factored, at least somewhat. So this implies A of n will now be n times the output per tree. I just wanted to phrase the problem in a way so you had to think about this. I could make it harder and have you have to come up with that, but this is fine. So now output per tree times the number of trees planted per acre. So this is the number of apples per acre, just to reinforce that. Okay, so there's our formula. So now we want to maximize, and we know we can maximize because we've got a negative here as the leading coefficient. But first, what we want to do is make it user-friendly. So let's rewrite it like we did in the last problem. So we have n negative 17n plus 1,870. And let's factor the negative 17. So we'll have negative 17n times n. And so here we need what? Plus 1,870 divided by negative 17. So we have negative 17n, and these numbers work out okay. So if we look at this, 17 into 18, that'll go one time. And then of course that leaves a 17 behind conveniently, then a 0. So we get, well, I don't need the fraction bar anymore because it divided evenly. Okay, so when we look at this problem, we're thinking, well, this was a little bit easier than the last one because by virtue of how it was set up, you actually get the factored form. All you want to do is clean it up a little bit. Now we can say this equals 0 if and only if n is 0. We knew that for free, or n equals 110. So now the midpoint will be what? 0 plus 110 divided by 2. So that's 110 divided by 2, which will be a 5 and a 5. So now we can see that this is the so-called H. That is, we need 55 trees per acre to maximize, in this case, the production. So plant 55 trees per acre to maximize production. So this is the quadratic functions can be deceptive at times. It's like I've said before, if you own a business, like you own a hotel, you don't want that hotel to be, no vacancy. You'll lose money. The thing is that there's a give and a take with quadratic functions. And there's always a optimal number of vacancies that help you to make more money. So when you consider this is a little bit more intuitive. If you crowd the trees too much, then maybe they don't get enough sunlight. Maybe they don't get enough water. Maybe there's not enough carbon dioxide. So crowding can be bad. And then, of course, you can spread your trees out a lot where they have all kinds of room, but then fewer trees is lower yield too. So you have to, as farmers really are actually mathematicians of sorts, they have to be able to think quantitatively, and they use their experience in farming, and then, of course, their knowledge of agriculture from previous generations that has been passed down to them. So now, let's go ahead and compute this. So what is the actual maximum in this case? How many apples do we get? And I think I actually computed it. It's a lot of apples. So now, A of 55. And I think what I did here is I utilized, I used some symbolic computation. Yeah, that's what I did. Here we go. So now here's our formula. Yeah, interesting. So now we have negative 17 times the 55. And then of course now we have 55 minus 110. But that's also a negative 55. So we have negative 17 times 55 times a negative 55. Now what we see, these are always fun because the arithmetic is married to the algebra. So we get what? Negative negative is a positive. So we get what? 17 times 55 squared. Now, here's something that we can actually do to make this problem somewhat doable with symbolic computation. That is, we can rewrite the 55 as 50 plus 5. So here's another trick you can do to improve your arithmetic skills. So we'll have 17 times, and use the binomial theorem, 50 plus 5 quantity squared. So we get 17. So we square the binomial, 50 times 50, that's 2,500. And then now, of course, we say 5 times 50, that's 250, and double it. So that gives us a 500. And then, of course, 5 squared is 25. So now what I found is easiest here when you're teaching symbolic computation, say you're tutoring someone and you're doing this by hand, you can say, okay, I can break this down. These are fairly simple and I don't want to work too hard here. So what I can do is now write 10, that's an easy number, 2,500 plus 500 plus 25, and then plus 7, 2,500 plus 500 plus 25. So that makes the computation very simple. So now at this point, we can go ahead and add this because it's easy to multiply by 10. So we get 10. So this will be, in this case, a 525. So we have 2,500 plus 525. We have the same over here, so we'll just repeat that calculation. So we have 2,500 plus 525. And now let me move this to another sheet. So now, if you will, this equals, so we've got, add these numbers, 10. So that's just going to be a 2 and a 5. 5 and 5, a 0 and a 1. So that's 3,025 plus 7 times 3,025. Just like we're doing our algebra with our numbers. So add a 0, so that's 30,000. In this case, well, 30,250. Just add a 0 plus. And now let's multiply this out. So that'll be a 5. And then we need a 3. So that's a 7 and a 1. And then, of course, a 21. So now we can add this up. This will give us a 5. So we've done this. And then this will give us a 12 with a 1. So that'll give us a 4. And then a 1. And then a 5. So we get 51,425 apples. Now what I want to show you that's important here is the analysis that I continue to do. When I asked my Calculus 2 students to compute the volume of a solid that has square cross sections, and the base is bounded by a linear function and a quadratic. And they have to square a trinomial. And then they end up with computations that look like this. And there's an inability to do the arithmetic because they're so used to just plugging into a calculator. So what I'm trying to show you here is that if you take the time to basically look at what the numbers tell you to do, it's basically what the letters tell you to do up here. And so in order to get better at mathematics, because all of you all are very good, I look at your WebAssign and I'm very impressed, is that we can now look at the numbers like we do the actual letters. So of course there are times when we get an exact answer and we need to approximate some things. When we get to trig, we'll have to do some approximations because the trig functions are transcendental and exponentials are too. But we want to be able to compute symbolically when we need a good answer, so to speak. We need an answer that supports the problem. So think about this particular problem and just note that what I've tried to do here is give you an alternate method. That is, when we have quadratic functions that do not have a constant term here, we can factor and take the midpoint to find the h. So in this case, we get the h first, and then we take the simple formula that we managed to produce here to find the k. So remember, this is the k. So when we're doing these types of problems, what's important is that you see that the calculations can vary dependent upon the approach, but the result is the same, okay? So when it comes to doing quadratic functions in the WebAssign, practice finding just the maximum, produce the k. Practice computing the square or completing the square. And with the one-to-one functions, I just want to give you one more example here, just illustrate it. I had an example that I wanted to share with you. As in closing, and this is what I wanted to talk about with the one-to-one. Here's an example from your, I did some computations here with another problem, but I ended up with the golden section, and I said, well, I'll let them worry about this. This will be when we do synthetic division and all that, and this is a very pretty problem, but a little bit too complicated for you all right now. So I won't talk about that. But I want to give you a little example here of what I was talking about. Here's a WebAssign problem. And so Marcello's Pizza, he sells a large pizza for $19. And he charges $1.50 for each additional topping. This is the case where we want to preserve the letters. And I want to show you how you can preserve the letters and then maybe move to a different letter, like we did with the graphing. First, we want a function that models the price of a pizza with n toppings. Okay, so this is additional toppings. So n is greater than or equal to 1. So that would mean the base cost plus 3/2, 150 times n. So that's the function, okay? So then we want to compute the inverse function. Well, we like these types of functions. They're clearly one-to-one. They're just lines. You can set your f of a equal f of b. It's clearly one-to-one. Now compute f inverse. Well, what do we want to do? I'm going to think of this as just a y, and we want to solve for n. So we write this equation here and solve for n. The first thing we do is subtract 19 and then multiply by 2/3. Now, you're thinking if you're doing this problem, this is so much better to leave in this form because this is the number of toppings on the pizza that cost y dollars. So when you think of an example like this is what I was talking about. you don't really want to switch the letters around, because now if you solve for n, you can input the price that the customer paid for the pizza and figure out how many extra toppings they ordered. I mean, you know, it's not a mind-blowing problem, but this is what I'm talking about. It's better to preserve the letters here. Now, if for some reason we wanted to plot these on the same set of axes, we could just interchange the n, y and the n, and write this, kind of like we did when we were graphing functions on the same set of axes. But this is an example of where it's nice to go ahead and preserve the original variables, because WebAssign will say, well, what does this represent? Well, you can say it's the number of toppings, the number of additional toppings, because the letters tell you that. The idea is when we don't preserve the letters and we start interchanging them, doing an applied example, we get confused. And even when we start working with inverse trig functions in calculus, we'll be sure to make sure that we preserve the letters so we know the restriction on each letter. And then we can move to a more user-friendly formula like this. So this is what I'm talking about. Mathematics contains so many conventions, but we have to maintain some understanding of what we're doing. And if we don't, then we start guessing. And when you start guessing, that's not good. When I do my own work, I think of things that I need to do to move forward in what I'm studying at the time. And I apply the same methods that I tell you all. So go ahead and work on these ideas. Again, you'll find this simpler than those word problems from last week. And I will have some information up about the test. It will be a WebAssign test, and you'll have a large enough window to be able to complete it. So I think it'll be very user-friendly. I appreciate your attendance today. Thank you for your attendance. Thank you for your hard work. Remember, our goal is preparation for calculus. Calculus 1, Calculus 2, and 3. And we will find that to be a good experience if we put the time into this class. So everybody have a great day. If you want to come to office hours at 3:15 today, I'll send out an invitation and you're welcome to join. Otherwise, good luck with your studying. Have a great day.
Have a good day.
Bye, everyone.
Thank you.
Thank you.
Thanks.
I think you all must be happy people because you're taking a math class in the morning. So that makes you rather distinguished.
Thank you.
Thanks.